Okay, so in this somewhat shorter section, we're going to kind of go back to the idea of like sitting in front of a wood stove or sitting in front of a burning piece of firewood, and ask, how does heat actually move from one place to another? How does the heat from the fire actually get to our faces or our bodies, so on and so forth? So there are three primary ways heat or thermal energy moves from one object to another or within the same object. And so in this section, I'm going to kind of qualitatively describe each of these three mechanisms. And in the next section, when we talk about insulation, we'll get into a little bit more quantitative detail. But for the time being, I want to kind of give you a qualitative picture of what each of these mechanisms are. So okay. First, we'll start out in section 8.2.1, talking about the conduction of heat. Conduction of heat. So conduction is the flow of heat through a material. Flow of heat through a material or from one object to another object it is physically in contact with. Another object it is physically in contact with. Okay. And the idea here is that heat is going to move from a hotter part of an object to a colder part of that object, even while all of the atoms and molecules involved in these solids stay in place, right? So in conduction, you have no overall motion of molecules, but you still have heat transported from one part of a system to another. So let me kind of illustrate this by bringing back my cartoon of a nice regular lattice of atoms, say in some solid substance, so in a solid. And let's suppose that, this side of the object is really hot. Maybe this is an iron poker or something, and I've stuck that end in the fire. And this end of the object is relatively cooler, right? So, it's the part of the poker that I'm actually holding, hopefully. So what goes on in this kind of situation where one part of an object is actually hotter than a different part of the same solid object, right? Well, this part of the hotter object, the atoms over here are kind of wiggling and vibrating, kind of quite a bit more than the amount that the atoms over here are wiggling and vibrating around, right? And so, the atoms over here are kind of vibrating and oscillating more than the atoms that they're sitting next to, right? And so what that means is that, as they kind of wiggle and bounce around, they are going to kind of start pushing against the kind of less oscillating atoms that they're sitting nearby, right? And that's going to transfer kind of tiny microscopic amounts, collisions, or transfers of momentum, so on and so forth, right? And so as the atoms over here are kind of wiggling a lot, and these ones are wiggling not too much at all, eventually some of this wiggling motion is going to get transferred into, oscillating motion of this next layer of atoms, until on average, atoms that are side by side are kind of oscillating and wiggling by about the same amounts, right? And so kind of atom by atom, layer by layer, thermal energy gets transferred through the kinetic motions of each layer of atoms from a hot place where the atoms are vibrating a lot to a colder place where atoms are vibrating a little bit less, right? So this is a mechanism where, like, atom by atom, heat can be conducted through a solid object. It turns out metals are particularly good thermal conductors because there's another way that they can conduct thermal energy. So metals are especially good thermal conductors because they have mobile electrons. That's actually the thing that makes metals good conductors of electricity in the first place. So what happens, is that you have the, say, nuclei of a bunch of metal atoms in a wire. And some of the electrons that would usually be associated with each individual atom form a kind of mobile band of conducting electrons, where the electrons that used to belong to some individual atom are now free to kind of travel really quite long distances all across the metal. Right? And what can happen in this kind of, why does that help heat transfer? Well, these mobile electrons can like pick up a little kick by, bumping into one of these heavily vibrating atoms, and then like travel a long distance before they bump into a different atom. So they pick up some momentum by colliding with a hot atom, and then travel a long distance, skipping a lot of these atom by atom layers before they deposit some of that thermal energy into a different nucleus. Right? So the fact that these mobile electrons can like travel pretty far before they drop off, a little packet of thermal energy, is why metals are such good conductors of thermal energy. Right? And so for the most part, substances that conduct electricity well tend to also conduct heat really well. In lecture notes, I comment that one bizarre exception to this rule is diamonds. Diamonds are really bad at conducting electricity. They turn out to be really good at conducting heat. And actually, jewelers can sometimes use that fact to distinguish a fake diamond from a real diamond by asking how quickly does heat flow through the gemstone when they apply a gradient of temperature across it. Okay, so heat conduction, again, the idea is that it occurs when two objects, a hotter object and a colder object, are actually in contact, or if one object has a part of the same object which is hotter than a different part. And what happens is that since temperature is like this measure of internal kinetic energy, the internal kinetic energy within an object tends to equalize across the whole object by this bucket brigade of, handing off via tiny collisions, microscopic amounts of momentum, or depositing little bits of average kinetic energy from the more oscillating parts of a material to the less oscillating parts, until on average they're all moving the same amount. Okay, so that's conduction. Another really important mechanism of moving heat around is convection. Convection of heat. Okay, so convection is refers to heat transported by a moving fluid. Okay, and let's think about that in the context of we've got a room, and we've got like a little wood stove over here. Okay, so this wood stove is quite hot, right? The fire is roaring, hopefully, and so this wood stove is in direct contact with the air molecules around it, right? So it conducts some of its heat into warm air around the stove. Warm air, okay? Immediately next to the stove. Now, in the section on fluids, one of the things that we learned is that warm air, if it's at the same, pressure as the air around it, warm air is less dense than cold air. And so this warm air will start to rise up, right? And the warm air that's here will start to rise up, and the warm air that's here will start to rise up. But as this air moves out of the way, it's not like there's suddenly going to be a vacuum where there's no air whatsoever around this wood stove. Instead, kind of colder air that was sitting somewhere else in the room kind of rushes in, moves in to kind of take the place of where the warm air used to be, right? And this will kind of set up a circulating current eventually, if you leave this running long enough, where the wood stove conducts heat to the air around it. That warm air rises up towards the ceiling due to buoyancy. Cold air rushes in to replace it, and you get this circulation pattern of warmer and colder air moving throughout the room. And so what you can see here is that, for instance, if you look at the ceiling, even though the air at the ceiling is not in direct contact with the stove itself, there's this motion of fluid which is carrying hot air, which is carrying heat towards the ceiling. Okay, and that's what convection is. Now, of course, if you're heating up a room and this is all you do, you just end up with hot air at the top of the room and cold air where you are trying to sit or enjoy your dinner. And so in actual room systems, you would install like a big fan that would spin around, that would blow still warm air down and create a better pattern of convective heating for at least the floor level part of the room. You might say this feels a little bit bland, but actually we've just explained why there's wind on Earth. Here's some land on, say, the shore, and up in the sky you've got the sun, shining down. You've got the sun shining down, and the sun's rays are warming up both the land and the water. But actually, because of the way that the land absorbs the incoming solar radiation, the land warms up by more than the water warms up. So there'll be this layer of hot air because the sun warms up the ground, and then the ground then warms up the layer of air right next to it. We get some warmer air. That warmer air starts to rise due to buoyancy, and relatively cooler air that was above the water rushes in to replace the warm air that used to be against the ground, right? That's what wind is. Wind is just a bonkers giant set of these enormous convection currents throughout the entire atmosphere that ultimately are coming about because of solar heating, right? Where surface winds are blowing from relatively cooler spots of the Earth to relatively warmer spots of the Earth, right? The physical details are really messy, but this basic idea of convection currents and convective heating is the underlying physics. There's one thing that I kind of glossed over when I was describing the sun's rays heating up the Earth, which is, what am I talking about? How is the sun heating up the Earth in the first place? And that's the third really important way of heat moving from one place to another, and that's radiation, radiative heat transfer. I'll just say radiation. Okay. So what's going on? In addition to these atoms physically wiggling and vibrating around, atoms can both emit and absorb electromagnetic radiation. Now, we're going to talk a lot more about electromagnetic radiation towards the end of the semester when we discuss what is light in the first place. But for the purpose of this discussion, let me just describe very qualitatively, shorter wavelength, longer wavelength, what I mean by electromagnetic radiation. So electromagnetic waves are propagating waves of electricity and magnetism, and they encompass a lot of the things that I know we've all heard about, in our daily life. So there are things like, radio waves, visible light is a type of electromagnetic radiation, X-rays, like you get at the dentist or the doctor's office, that's a type of electromagnetic radiation. There's stuff like infrared light. Maybe you've heard about ultraviolet light. These are all just different types of electromagnetic radiation, which are characterized by having different wavelengths. If I draw a wave, I can say, what is the distance? If I draw a wave and it just keeps going and going, you can say, what's the distance between two similar parts on this wave? So how long do I have to go, as it goes up and then down, before it starts going up again at the same point? This distance, as we'll learn a lot more about later on, is the wavelength of the wave. And electromagnetic radiation, there's all these flavors of different types of electromagnetic rays that are just characterized by different wavelengths. Okay, more on this in a few chapters. But what we need to know for heat transfer is that objects can both emit these different types of electromagnetic radiation, and they can also absorb it. And that gives a completely new mechanism for transferring heat across space, even if the object isn't in contact with another object, or even, separated from that object by another fluid. So even if this object and that object, there's no air in between them, you're just in outer space, electromagnetic radiation still lets you transfer thermal energy back and forth by emitting and absorbing these electromagnetic waves. Now, the type of wave you typically emit and absorb, so the types of waves, I'll just say EM waves, an object tends to emit depends on its temperature. And the way it works is that colder objects tend to emit, longer wavelength electromagnetic radiation, so typically infrared stuff. And hotter objects tend to emit higher wavelength electromagnetic radiation. That's why, if you have a hot coal, it glows red. It's emitting wavelengths, it's emitting electromagnetic waves in the visible part of the spectrum, and in particular in the red part of the spectrum. Hotter objects start to glow, red and then blue and then white as you get to longer and longer wavelengths of light that they tend to emit. Fantastic. So both the type of electromagnetic wave that it tends to emit, and also, as does the amount of EM waves. So hotter objects tend to emit both in a different part of the spectrum and also throw off more of this electromagnetic radiation. Okay, and even objects that aren't like visibly glowing are constantly both emitting and absorbing all of these kind of different electromagnetic waves. It's just that cold objects tend to emit in the non-visible part of this spectrum of electromagnetic radiation. Okay, so whenever two objects, say, have a line of sight to each other, so suppose I'm standing over here and there's like a roaring bonfire over here. The fire is emitting electromagnetic radiation and those waves are bombarding me. And at the same time, I'm emitting, shorter wavelength electromagnetic waves, throwing off into space. And even though we're both me and the fire, constantly emitting and absorbing these electromagnetic waves, because the fire is hotter, it's emitting a lot more of them. And so the fire tends to warm me up as I absorb more radiation from the fire than I emit. And the fire, is receiving less of the thermal radiation I'm putting off than it's emitting. Okay. This is one of the ways that, if you're standing in front of a fire, you can tell that thermal radiation is really important, and even more important than convective heating is, if you're in front of a fire and you put your hand in front of your face, the portion of your face that's shaded will suddenly feel a lot cooler. And that's because the actual air in between you and the fire doesn't warm up by as much as maybe you think it does. The direct radiation of the fire hitting you is really what's creating a lot of that sensation of warmth on your face. Okay. So that's kind of a qualitative description of each of these three main mechanisms by which heat can transfer from one place to another. There's this direct conduction of heat, which requires, atoms to be physically next to each other. There's this convection of heat, which requires an intermediate fluid to transfer heat for you from a hot object to a less hot object. And then there's this direct thermal radiation piece. And in the next section, when we talk about insulation, we'll get into a little bit more of like the quantitative details behind each of these three pieces.